Please join me in welcoming to the Mars stage Matej Chokalia. Welcome, Matej.
Thank you. Good morning, everybody. It's a terrific honor to be here to tell you about our work on robotic manipulation. Versatile dexterous robotic manipulation is what I also work on. And it's very much an open problem, right? We have many, many domains where we'd like to put robots to do manipulation tasks, because to have a human there is dangerous, it's expensive, or maybe it's just dull. And the fact that we still have humans do manipulation in all of these domains just shows us we haven't solved that problem yet. Particularly when there's a lot of clutter involved, where you have to reach into a pile of objects. You go into your pocket, you have a couple of things in there, you take one of them out, other things don't fall, you put it back. That's the kind of task that we don't yet know how to do. And we've just seen in the previous talk, and we've seen over the last years, impressive advances in reinforcement learning, deep reinforcement learning. So why is it that we can do so well at abstract intelligence, but we're still not there at embodied intelligence, right? Once it comes to going away from the bits and actually interacting with the atoms of the world. What is it that makes embodied intelligence so much difficult than abstract intelligence? And a lot of that has to do with the fact that the hardware matters. The actuators matter, the structure, the kinematics of your manipulator in the case of manipulation. This is illustrating it with the human hand. The human hand is such a marvelous piece of technology. We've seen here incredible feats of engineering. To me, the human hand is right up there in terms of its just technological capabilities. Sensing matters so much, right? When you're working on abstract intelligence, the state of the world is known to you. It's given. It's clean. It's very well defined. The real world, when you're manipulating in clutter, is a mess. And it's a mess that you have to sense, ideally with your onboard sensors, if you're going to be deployed as a robot, without external sensors acting as oracles. And of course, learning plays a huge role, but it's just one piece of this ensemble that makes embodied intelligence tick. And for us, we have the benefit that all of these things evolved together at the same time, and that interplay between them has evolved together. And I'm going to talk to you about today about two aspects of manipulation, two things that we work on in our lab on different sides of this spectrum. The first one has to do with the kinematics, the structure of the manipulator, and the application is manipulation in orbit. And we are looking at the International Space Station, a complicated, messy environment. It's not some sort of, like a clean room-like you might be inclined to think, and a lot of manipulation tasks to be done on the space station, chores, essentially, right? And the folks at NASA have, for a long time, tried to have as much technology out there to simplify the astronauts' life, to take some of the chores away from the astronauts. This is the AstroB robot that the folks at NASA Ames have developed. This is an assistive free flyer. It's a cube about this big, designed to float around the space station. Originally, it was meant just as a monitoring, surveillance platform. It has cameras, it looks around, it helps astronauts with monitoring the space station. We are working with NASA to put manipulation capabilities on the AstroB, and more specifically, versatile manipulation capabilities, okay? We've already worked with the folks in the Intelligent Robotics group at Ames, and we've designed a perching gripper for the AstroB to grab onto the handrails, of which there are plenty on the space station for astronauts to use. But we'd like this manipulator to be significantly more versatile, okay? So what kind of manipulation tasks would there be on the space station for a robot like this to do? I am lucky to be colleagues in mechanical engineering at Columbia with Mike Massimino, who's sitting right there, former astronaut, one of the people who fixed the Hubble telescope. So he knows a lot about being in orbit. And we brainstormed and came up with a number of use cases, various things that would be useful for a robot do up on the space station so that the astronauts don't have to do it. Things ranging from switchboard operation, object retrieval, food items, tools. And they all highlight the need for versatility. You need a reasonably versatile manipulator up in space. Okay? But then therein lies the rub, right? Because the entire AstroB is about this big. The payload bay, where you have to fit the arm and the hand, is tiny. How are you going to get a versatile hand into that tiny, tiny space that the AstroB affords. And this is where we came in, trying to look at the kinematics of the manipulator and how we can make this happen. This is what we came up with. This is one of the early prototypes. It's 3 fingers, it's 8 joints. It's a single actuator, right? And this is a very early prototype. We didn't put a motor on it yet. You can see just a person pulling on it. But it's a single motor that's driving all 8 joints, all 3 fingers. And because of the mechanical design, the kinematic optimization, it's cycling through all of these grasp postures that enable it to interact with all the objects that we care about. And all the grasps that it can execute, not only it can reach the posture, but all these grasps are stable, and which means that it can actually act as a gopher and transport these objects around. Okay? And again, all of this is just from the actuation. It cycles through these poses. You get this synergistic behavior between the joints with a single actuator that's connected with tendons to all of those fingers. Okay? So how does this happen under the hood? We had this intuition from the beginning that to get the kind of versatility we wanted 3 fingers, we wanted 8 joints. Okay? So this hand has what we call an 8-dimensional posture space because it has 8 independent joints. So anytime the hand is in any specific posture, that corresponds to 1 point in that 8-dimensional posture space where each axis corresponds to one of the joints. Okay? That's my best attempt to put an 8-dimensional space on a 2-dimensional slide. Then, when you think about all the grasps that you'd like this hand to execute, each of them defines 1 point in that 8-dimensional space. Okay? Then you introduce what we call underactuation. We are not going to be able to put a hand with 8 motors inside the AstroB. It's just not going to happen. 1 motor, maybe 2, probably 1. So if you have a single motor that's connected with tendons to all of these joints, that introduces what we call a manifold in this high-dimensional posture space. Yesterday, in Daphne Kohler's terrific talk, she was also describing these low-dimensional manifolds, very much the same concept. So what we did, our design optimization methods shape this manifold introduced by underactuation so that you can hit all of those points that you care about, you can shape the hand, and you can execute all of these grasps. The intelligence goes into the mechanism itself, so then at runtime, there's nothing for you to do except pull on that one actuator. The student leading this project, Tianjin, likes to refer to it as a wise mechanical design, and I like that moniker, so we've adopted it. So let me show you how this works in practice. This is one more advanced prototype with an actual motor. So this is the hand that I have right here, and I have a single button. All I can do with this hand is just push the button, and then it closes the fingers, and I get this synergistic behavior that has been encoded into the mechanism at design time, so that at runtime, there is very little for me to do in terms of sensing and control, because on the AstroB, we're not going to be able to do that. So I can execute a fairly wide range of grasps. I can do what I call a fingertip tripod grasp. Yes, they do eat canned tuna on the space station. It can envelop and do what we call a power grasp around small objects, things like tool and so forth, which is important for grasp stability. It can also go ahead and do what we call a power spherical grasp for larger objects and envelop the fingers around. And again, all the intelligence is in the mechanical design because the specifics of this task being on the AstroB mean we cannot afford to do much in terms of sensing and independent control live. So we have no choice but to package the intelligence into the embodiment itself. So this, of course, is me operating the hand. What will this look like on the AstroB? Who's going to operate it? How autonomous is it going to be? Is it going to be teleoperated? One thing I can tell you for sure is that it won't be the astronauts teleoperating the AstroB, because that would defeat the purpose of relieving them from having to do all of this stuff. So one option would be to teleoperate from the ground. And here what I have running on my computer is a teleoperation interface where I am controlling live this hand in our lab at Columbia, so across the country. This is happening right now. And yes, this is running inside a web browser. This is just Firefox. And through this interface, I can go ahead. We have the hand. It's not on the AstroB. It's just on a robot arm that's pretending to be the AstroB. I have a couple of cameras that I'm using. There's a camera, an external camera, and then one more that's inside the hand itself. And I can use the perspectives from both of these cameras to position my hand and do various manipulation tasks. Okay, so I can do pick and place. I can move objects around. And you can see that it works. It's a fairly tedious process, difficult. And furthermore, this is with me. This is just with the latency that we get just across the country over the internet. There is some latency here, but it's nowhere near the kind of latency that they actually have from surface to orbit with the AstroB. So in those cases, they tend to get more like 2 to 4 seconds round trip time. So both because this is a relatively slow teleoperation interface and because the round trip time with orbit is much bigger, this is not what the actual AstroB operation is going to look like. And what we're doing right now is we're developing what we call a shared autonomy interface, where the AstroB is going to be mostly autonomous. And the hope is to have it call the surface only when it detects that the probability of success of the autonomous manipulation algorithms are too low to be acceptable. And then it calls home, and the operator, rather than doing this kind of bilateral teleoperation, low-level teleoperation that we have now, the operator will just supply enough information to increase the probability of success of automated manipulation above the acceptable levels. So that kind of shared autonomy interface is the next step for us. And then we will continue integrating with NASA. We are hoping to start testing with the AstroB in simulated microgravity at Ames. Then flight certification, because of course we're not going to send in orbit something that can catch fire spontaneously. And then we will have a versatile manipulator inside the space station, which hopefully is the next step for this. So let me switch gears now and talk to you about the other end of the spectrum in terms of manipulation capabilities. So far I've talked about putting a lot of the intelligence in at design time, because at runtime you cannot afford to have a lot of sensing and a lot of independent control. For many applications, like manipulation in heavy clutter, you do need that level of control and sensing. And hopefully, thankfully, you're not subject to the same constraints. Okay? So let's talk a little bit about the kind of sensing that we have in the human hand, the kind of tactile sensing that we have in the human hand, a huge enabler for our manipulation capabilities, right? Again, the human hand, underappreciated piece of technology. In every fingertip, you have 600-700 individual mechanoreceptors that give you information about touch. Each of those mechanoreceptors, imagine 600 of them in the fingertip, each of those individually wired, giving that information back to your nervous system. I'd love to be able to do that in robotics. We don't know how to do this kind of sensing development in robotics, to individually wire those many tiny mechanoreceptors. And there's more to it, right? It's not just on the front of the finger. On the back of your fingers, where skin has this beautiful accordion structure so that it can go over joints, even that is sensorized. In robot hands, to get away from these wiring problems, we can build these tactile arrays. They're good. They don't cover edges and corners. We cannot sensorize the entire complex shape of the fingertip. And if you have edges and corners to the finger that aren't sensorized, when you dunk your finger into a pile of stuff, guess where you're going to make contact? On the edges and on the corners, exactly where you don't have the sensors. So we've been motivated to build tactile sensors that have the same ability to do spatial coverage and ideally the same acuity as their human counterparts. And the method we use is somewhat surprisingly optics, right? You'd say, wait, optics for tactile sensing, those are different modalities. So let me walk you through how we build our tactile sensors. It starts with a flex board. This has on it LEDs and photodiodes. This is a photodiode. This is a pair of LEDs. In total, there's about 32 LEDs, 32 pairs of LEDs and 32 photodiodes. So we have the flex board. Then we 3D print a skeleton. We put the flex board origami style on top of that skeleton. And then on top of it all, we mold a layer, about a 7-millimeter thick layer of transparent rubber. Okay? This is with the LEDs turned on. So now, imagine that one LED is on. We coat the whole finger in a reflective layer to keep light in. So then with one LED on, one photodiode receiving that signal, when this finger touches something, how light travels between the LED and the photodiode changes. So we get a signal, okay? But that's one LED and one photodiode. And we have 32 LEDs, 32 photodiodes. So we get 1,000 signals out of this fingertip with a relatively small number of wires, okay? So this is showing just, I think, 60 of those 1,000 signals. This is the finger coated in the reflective lid. It's silver dust. It's makeup. People wondering why my lab buys so much makeup at Columbia. And the finger is being poked, and the signals, the 60 signals change because of touch, okay? So we get a very, very rich signal set with very few wires, which is one thing that we wanted all along. Of course, though, it's also a very complicated signal set to make sense of. You're not going to be able to build analytical models of how these signals react to touch. But thankfully, we don't have to build those analytical models, okay? So again, this is an example of multiple technologies coming together at the same time, where advances in flexboard technology, the hardware, but then in the age of machine learning, we are now able to learn how to make use of this data, something that we wouldn't have been able to do maybe as recently or 6 or 7 years ago, okay? So we just use learning directly on top of this to discriminate and to regress to the things that we care about. Of course, for machine learning, you need training data. That's a thing that's somewhat easy to overlook. So how do we collect our training data for this fingertip? This is our setup for training data, where we have a 6 degree of freedom robot arm that is poking our fingertip in very, very controlled fashion. So we know for this training data, we know the location of where we're touching the finger. We have a load cell on top of this very precise linear probe, so we can get information about contact force, and this allows us to collect the training data that we need. And this is an instance of a robot arm that is poking an artificial finger in order to elicit tactile sensation. And in fact, we have all seen this as recently as last night. I've always had this slide in from the beginning. I had my thunder stolen from me. But if somebody's going to steal your thunder, let it be Luke Skywalker, okay? So let me show you what it looks like once we have trained our learning algorithms. And this is the very first time we are showing this fingertip. And it has learned to discriminate the location of the touch and also the magnitude of the force. The size of that sphere is proportional to how hard I'm touching. And one thing, again, that we're very happy with is that, so we have this cylindrical front, 190 degrees around the circumference are sensed, and then we have the hemispherical tip, and the entire hemispherical tip, just half of a sphere, that is completely sensorized. There are no hard edges or corners that we wouldn't have tactile data from. So this is very, very well suited for manipulation in deep clutter, where we can make contact anywhere, and the hand would still be able to touch, to have information about location of touch and also the magnitude of it. And by the way, I invite you to come to the lawn during lunch, and there you can play with our hands for the AstroB. You can teleoperate our hands in the lab at Columbia, and you can also see our tactile fingertips at various stages of construction and get a sense for what they look like on the inside without the silver dust applied. So this is still ongoing work. These results, we're very much working on them. We don't yet have the data. We're hoping that we will very soon. But we believe that this is the first fingertip that will have human-like acuity, tactile acuity, also with coverage of complex curved surfaces, no hard corners, no hard edges, and high sampling rates. This one, all 1,000 signals are being sampled at about 60 hertz. We're hoping to go to about 200 or 300 hertz in the future, which we have a feel is what we need for dexterous manipulation. So to wrap it up, what we're seeing is these parallel advances in all the technologies that have to do with embodied intelligence, right? And again, 6 years ago, the circuitry wouldn't have been possible on this, the learning wouldn't have been possible on this, but now they are, okay? So it's together, all of these fields advancing at the same time is what we strongly believe will give us the ability to do complex embodied intelligence tasks like dexterous manipulation. Thank you.